everyone. My name is ManikaMishra. I am a third year undergrad computer science student at ManikaMishra University. My mentor is Dr. Rajiv Chaudhary. Today we are going to talk about human posture recognition system. So let's start. Human posture recognition system. Going towards the content table. It has introduction, what is human body posture recognition system, depth imaging, and RGBD camera, the proposed method, 3D skeleton estimation, computing features, geometrical angles, posture classification, experiments, results and discussion, use of human posture classification system, and references. So coming towards what is human posture recognition system? Human posture classification system classifies human posture in standing, bending, sitting, walking, and crouching. The model uses depth imaging by exploiting the depth information captured by an RGBD camera. What is depth imaging? Depth images are the pictures of object which is human body in three dimensions including length, width, and depth. RGBD camera sensors are specific type of depth sensing devices that work in association with a RGB red, green and blue color sensor camera. So coming towards the proposed system. Our system uses a single RGBD camera to capture depth maps and build a body skeleton. We then use the 3D joint positions to compute posture features including the 3D pairwise joint distances and the geometrical angles defined by adjacent body segments. A supervised classification method is finally applied to recognize static human postures. In summary, the system consists of three main modules, which is skeleton estimation, feature computation, and postures classification. 3D skeleton estimation. To build the 3D model of human posture, we used the skeleton detection method to localize different body parts. This method is quite accurate in modeling the human body as an articulated structure of connected segments. This can be achieved in real time by the only use of depth images. The method of Shorten et al. Uses a random forest classifier to segment the different human body parts through a pixel level classification from single depth images. A mean shift mode detection is then applied to find local centroids of the body part, probably mass, and generate the 3D locations of body joints. The obtained 3D skeleton formed by 25 joint represents the human posture as illustrated in the left side of the slide. Picture in the left side of the slide. Now, computing features. Constructing a robust feature set is a crucial step in posture recognition system. In our work, we used two types of features to represent human postures, the 3D pairwise joint distances and the geometrical angles defined by adjacent segments. Considering the set of n equals to 25 joints, the 3D joint coordinates are extracted as x equals to ji, xi, yi, zi, I equals to 1 to n, where ji is the joint number I obtained from the body skeleton. Once joint positions are extracted, we compute two types of features representing human body posture. Number one, the 3D pairwise distances between the joints, and number two, geometrical angles of adjacent segments. Joint distances. Given the body skeleton obtained from depth images, we calculate the relative 3D distances between pairs of joints. Such features were successfully used to model human body for action recognition. We calculate the feature vector as t equals to distance ji, jj, ij equals to 1 to n, where distance jj is the Euclidean distance between 2 points ji and jj. So, how to remove the scale invariance and body height invariance? To ensure scale invariance, the 3D distances are normalized with respect to the person's height. The normalization process is performed by considering the distance BP. BP is the 3D distance between the spine shoulder joint and the spine middle joint. The choice of this segment is based on experimental observations, concluding that the distance BP is sufficiently stable with respect to several body deformations in addition to its proportionality to the person's height. Now, coming towards geometrical angles. In addition to 3D joint distances, our joint-based features include geometrical angles corresponding to relevant joints. Based on a dataset, we selected experimentally a subset of joints according to their importance in characterizing the studied human posture. In the figure, as shown in the slide, the selected joints are represented in red. We considered M equals to 12 angles as follows: CBCP, CPCD, CE, CP, CD, CF, DF, EC, EG, DR, TF, ES, EG, PC, PQ, QT, QU, RT, RQ, SQ, SU, and QR, QS. Geometric angles defined by adjacent segments are directly estimated from joint positions. We define the geometrical angle feature vector as A equals to theta k uv, k equals to 1 to k. A, the angle theta k between the two adjacent segments u and v is calculated using the 3D coordinates as theta k uv arc cos u dot v slash absolute of u dot absolute of v. The two feature sets D and A are then concatenated in a single feature vector to find final representation of human posture F equals to dA. Now, coming towards postural classification. Once the body posture is modeled, posture recognition is performed in a supervised classification approach using SVM classifier. With its different kind of kernels, SVM has the ability to generate non-linearly as well as high-dimensional classification issue. The SVM classifier also supports multiple class problems by computing the hyperplane between each class and the rest. In this, we used an SVM with a linear kernel since it outperformed other classifiers. The postures are classified into standing, bending, sitting, walking, and crouching positions. Now, experiments. The dataset created is called KSRD, Kinetic Posture Recognition System. The camera is mounted on a tripod placed in a corner of the laboratory. It is considered five classes of postures: standing, bending, sitting, walking, and crouching. Each posture was performed by 10 participants of different ages, gender, and morphological characteristics. In order to increase the variability of the dataset and evaluate the system in handling scale and orientation changes, each posture is captured at four different orientations and four different distances with respect to the camera. The distance varies from 1 meter to 4 meters, while the orientation angle is changing between 0 and 360 degrees. The dataset includes a total number of 800 observations, and that is used for training and testing the proposed system. The dataset is randomly divided into training and testing set using the k-fold cross-validation method with k equals to 10. The figure shows the examples of human body skeleton corresponding to the five classes. Now, coming towards result and discussion. We designed our experiments in order to analyze the performance of our method according to several aspects. The first experiment set aimed to identify the optimal choices regarding the two main components, the feature set and the classification method. We thus investigated several choices implying five classifiers: linear discriminant, quadratic discriminant, linear SVM, quadratic SVM, and cubic SVM, and the three feature sets: symmetrical angles, pairwise joint distances, and the combination of two types of features. The investigation showed that the linear SVM applied to the entire feature set achieves the best recognition rate, which is 88.3%. We base our recognition system on number one, linear SVM classification and the combination of two types of features. Now, I would like to conclude that we learned a novel method for human posture recognition using an RGBD camera. The method included three main steps: skeleton estimation, feature computation, and posture classification. Firstly, a 3D skeleton is estimated from depth images. Joint-based features are then computed for modeling the observed human pose. Posture classification is finally carried out using a linear SVM. The method, the proposed system demonstrated high recognition rates and a significant invariance to important perturbation factors including scale, orientation, and illumination changes. So, why we need human posture recognition system? Human posture recognition system is gaining increasing attention in the field of computer vision due to its promising applications in the areas of personal healthcare, environmental awareness, human computer interaction, and surveillance systems. These are the references from where I have taken the information, and thank you so much for watching the video.